Hello, friends. So, just going to get right into it. I'm not going to be on video. This is all going to be whiteboard stuff, but we are going to try to cook through some stuff before the end of the semester. I'll tell you more about that when I see you on Wednesday. But today we're going to knock out normal subgroups and factor groups. We've talked about this. I've hinted at this already a little bit. So none of this will be shocking, but some of it will be incredibly cool. Oh shit. So I've got some kind of bad connection bullshit there. All right, let's get going. So we have this subgroup H of a group G, and we've talked about the left cosets and the right cosets not always being the same. We actually looked at an example, I believe, from D4 or S4 that showed that this isn't the case. So I'm hoping you kind of remember that. But in general, these are not the same set. However, if we have that the left coset of A is equal to the right coset of A for all A in G. So you can construct the coset left or right, you get the same collection of elements. If that is the case, then we say H is normal in G. And we write H with this little triangle. So it looks like the subgroup sign just cut off at the end like that into a triangle. We write H is normal in G. And now, some things to note here. This doesn't mean that AH equals HA for all H and H. What it does mean is that if I've got this element AH in this left coset, so H is an element of the subgroup H, and I look in this right coset over here, then I can find some probably other element H prime inside here that is equal to this original product. So every one of these has a companion over here, exactly one companion over here, but it doesn't necessarily involve the same element of H at all. And that's a good thing to keep in mind. Now, if we're going to test for normal normalcy of a subgroup, we have a nice test that I'm probably going to ask you to prove yourself on the take-home final. But right now, I'm just going to state it. We can show that H is normal in G if and only if X inverse is contained back in H for all X in G. Now you can kind of like take this and right multiply by X and see something like this in there. Um, or you could left multiply by X inverse, and then you'd see something like this in there, which and since X can be any element of G, it could be X inverse itself, in which case you would get double inverses, and it would look a lot like right cosets are contained in left cosets, no matter what the representative X is. So in some ways, we can believe that this is true. It's not a great stretch at all. Let me see if my little auto scratch out is going to work. Yeah, look at that. All right. I don't know, that's just dirt on my screen. Yeah, probably. So we have this test that can determine if we can use to determine if something's normal. Now, little hint ahead, does this look remotely familiar to you? Just this structure where I have something like this forming. Where'd you see that before? Well, we'll come back to it again, so I'm not going to say where you may or may not have seen that. Oh, by the way, there is a handout in world class that you might want to grab. So maybe pause this video, go download that, maybe print it out. It'd be nice to have a printed copy for yourself to look at uh, as an example that I wrote out over the weekend that I wanted to talk about today. So let's look at a few examples and just kind of observations about normal subgroups. So first thing is that if I have an abelian group, then every subgroup is normal because everything commutes. So in this case, this literally is an element by element equivalence. And this is really the only case in which we would have everything syncing up. I think I'm gonna not get as strong, stay that strongly, but certainly if we do have commutivity, then this is going to happen, and those are always going to match up. So that's a good thing to keep in mind because we will be working with some abelian groups, quite a few actually, and looking at normal subgroups in there and doing something special with them that we'll get to in a few. Another example, so I have a group G. If I look at the center of G, now remember that that is the set of all elements in G that commute with everything else in G. So this is equal to the set of all G in G, such that GA equals AG for all A in G. So it's just the elements that commute with everything else. Certainly the identity is in there. And this thing is a subgroup of its own. We can prove that. We might have proved that already. I can't quite remember. But this is, again, the center of G. And it is always normal in G. So Z of G is always normal in the group G itself, and it come falls back on that commutivity of all the elements just in Z of G, commuting with everything else. So again, here you're going to get left cosets and right cosets being identical for the same representative. So hopefully that's kind of making some sense there. We've got another example, one which I'm not going to prove right here. But if I have the symmetric group Sn, then the alternating subgroup of even permutations is normal in S sub n. And so this is, we could maybe take a little example here just so you can see what I'm talking about. Let's say that I've got this element 132. And that's in A sub n. Remember, you can count that this is an even permutation. Can decompose it as two transpositions composed together. And also 1, 2, 3 is an element of A sub n. So if I want to show that 1, 3 A sub n is equal to the right coset, A sub n 1, 3, then I can grab these particular elements out and see that that's true. So in other words, 1, 3, 1, 3, 2, which is inside here, is equal to 2, 3. And over here, if I take 1, 2, 3 and multiply that by 1, 3 on the right, then you could verify this for yourself that I also get 2, 3. So notice that it's a different representative from the subgroup itself for the same representative of the left and right cosets. And the proof of this is a little bit more involved than I really want to spend time with right now because I kind of want to get to our main construction using normal subgroups. So assuming I have this group, subgroup H, that is normal in a group G, I can construct what is called the factor group G mod H. Notice how I read that. I read that as G mod H. So this is essentially the generalization of integer modular arithmetic taken to any particular group given any normal subgroup. So we've got to have that subgroup be normal to form this thing and hope that it turns into a group structure, or in order for it to be a group structure, H must be normal. So this is just the collection of all left, and we could do this for all right cosets if we wanted, because H is normal. But generally, we work with left cosets. It's the set of all left cosets of H in G. Now, some of these are going to be repeats. We've seen how this coalesces. These cosets form groups of things. They cluster elements of the group together, kind of like condensation, or water that's breaking into little droplets that are disjoint entities to themselves. The group structure that we have here is that if I take an element, AH, from G mod H, and I multiply that, and multiply again is a loose term. This might be plus, this might be actual multiplication, this might be functional composition, this could be something weirder than that. But the way we define this is that we actually operate on the representatives inside the group G and then form the new coset H. And with this and the normalcy of H in G, we get a group structure. So G mod H is a group under this operation right here. Let's take a look at some examples of this. Uh, First example is that if I take G is the integers and H is the multiples of 6 in the integers, so this is um, minus dot 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 minus 12 minus 6 0 6 12 18 blah blah blah. If I look at, so why is H normal in G? So I can immediately say this. Why is that so? Because this is all abelian, because integer operations are abelian. So because of that, I know that the subgroup is going to be normal in there. So we're good to go on that. And now we're going to form G mod H. And the way we do that is to look at all the cosets and until we find all the distinct cosets, and those are going to be the elements of this factor group. So, in other words, Z mod 6Z, what does that look like? You've done some work with this, so it's not going to surprise you that I find my cosets to be, well, what are they going to look like, right? They're going to be some element from the integers plus that set 6Z. And you're going to get a repeat when A is a multiple of 6, it gets absorbed into that set. When A is not a multiple of 6, it shifts that set. So what we end up with are the cosets 0 plus 6Z, in other words, just 6Z itself, 1 plus 6Z, all the way up to 5 plus 6Z. Notice how we have an additive group, so I'm using that plus symbol for my cosets. Now, these guys could be represented, as little symbols like this. Da, da, da. And if we think about the group structure we're going to have here, you're essentially getting the integers modulo 6. So, for example, what if I took 2 plus 6z and I added that to 5 plus 6z? what I'm going to get is 7 plus 6z because I only operate on these guys, right? I'm only adding these representatives. That's how we defined it. And then this is equal to 1 plus 6z, and that 6 just gets absorbed into here. So this is 1 plus 6z. In other words, 2 plus 5 equals 1. And you can see that that is essentially addition modulo 6. So what we get here is that G or Z mod 6Z is isomorphic to the integers modulo 6. You've seen this construction before, and I hope it's starting to feel like a very natural thing. Um, let's take a look at another example. Let's actually go to that sheet that I wrote up. So coming to the sheet, I wanted to do something with D4 because I like just being able to picture things. So at the top, I defined the group D4 by the identity, the zero rotation, nothing happens to the square. Rotation by 90, this will be clockwise. And then r squared is 180, r cubed is 270 clockwise. Tau is the flip over that diagonal line you see on the right. And I ended up labeling those corners so we can convert all this into permutation notation. But essentially, the second half of this group is tau operated on the first four elements of this group. And we can view this as a subgroup of S4 if we wanted, as opposed to thinking about it as the symmetries of a square in the plane by just notating where those vertices go. And you can see that right here, that I've got all those things kind of labeled out. It honestly helps me get the computations done properly. Otherwise, it gets a little confusing. So we're set up. I'm going to let H be the subgroup that's the identity and rotation by 180 degrees. Now, we can show that H is a normal subgroup in D4. And I don't show that here, but if you wanted to verify that for yourself, that wouldn't be the worst exercise you could undertake. That subgroup is normal in D4. All the left cosets for each representative are the same as the right cosets for that representative. Not in the same order, but the elemental composition is the same. So then I went through and I cranked out the left cosets of H and D4 and notice how these differ. They're essentially the element, you have H and then R squared times H, or you have RH times, and then on the right, that's equivalent to R squared times RH. And each of these coset pairings differ by an R squared on the H, operating directly on the H. You could verify this for yourself. It's actually pretty fun. I mean, I had fun with it. Maybe I even did it down here. Yeah, I did some of it. I showed some of it. So what is this saying? It says that we're taking things that differ by 180-degree rotations and saying those are the same. So we're modding out 180-degree rotations and two operations that differ by that. So the end result looks the same, except it's been rotated 180 degrees. We're going to say, that's the same thing. Now, this subgroup has two elements in it. The original group, D4, has 8 elements in it. If we look at the index, the number of distinct cosets of H in D4, we get that there should be 4 of those, right? You take the order of the group divided by the order of the subgroup, and that gives you the index of that subgroup in the group. So here we expected 4, and I kind of use that as a little bit of a guideline to work these guys out. So I use the left-hand representatives, the simpler form of the representatives. to create this little Cayley table here. So D4 mod H are those four elements. Notice that H, the subgroup itself, is now our identity element. Look at how it functions in the table. It is our new identity. We're basically saying all those things are zero, they're nothing. They're the identity element. They are identical. And then you work it all through, and you already should be able to recognize this pattern. Yeah, look on the right. I did a little bit of computation just to keep my sanity checked because I wasn't sure that what R tau turned into, and it turns out it's actually equivalent to tau R. And tau R, I needed to get that tau R form because that's what I've chose as my representative here. Um, so I'm always looking for one of those four elements, H, R, H, tau H, and tau RH. And you work this through and you recognize that as Z2 cross Z2. And I want to talk about something. So the notation we've been using has been with that cross product. I want to clarify and improve that because actually what an algebraist would say is they would first off they would use this symbol which is an external direct sum. It's the same thing, it's just ordered pairs. Whoop. External direct sum. So this is just ordered pairs of things from Z2 comma Z2 and you get like this vector of group elements. And then this forms its own Cayley table. And of course, this is the Klein 4 group. And we've said all that. And there's only two groups of order 4. There's this group or the cyclic group. Z4 itself, um, those are the only two groups of order 4. And here we see that Klein 4 group manifesting itself again. Now, I want to kind of show you an underlying structure here. So if we take the actual, this is on the back of that page or the second page that you've got there. If we take the original Cayley table for D4 and we organize it, so we reorganize the columns and rows so that they represent those cosets. So, here is the H coset, and here is the RH coset. Here's the tau RH, and here's the tau RH coset, and then similarly down this way. You can rearrange if you coordinate the columns and rows to look like your cosets, you see the Cayley table break into these blocks. So here's the H block. Here is the R squared H block, which is just, or yeah, it's either, what do I got here? Yeah, it's the R squared H block, which is actually just H again. And you see H running all the way down the diagonal. So spend a little time looking at this. It was really fun for me to make and really beautiful to see the results in the end. I did some of the computations down here. And again, what I'm trying to do is get everything back to one of those four representatives. So when I see something like R, R tau, R squared, I'm like, I don't know what that is. And so I just go through and do some algebra and crank out and turns into the tau R representative. So that's about it for those examples. I do want to show you one proof. Actually, I want to look at a couple of results next. I don't even know how long we've been going here. I got to take a look at this Zoom thing here. Well, it's not telling me shit. So I have no idea how long we've been talking. It doesn't matter. It's all good. Let's just get some more dotted paper out here. So one result, which is actually super cool. Remember that group, that's a little too hard to read. That group of inner automorphisms on a group G. And that was the set of all phi that were one-to-one and onto G. So bijections of G onto itself that were of the form for each element G, they look like this, GX, G inverse. So all the maps that look like this for some G and G, let's put a little sub G there. That was the collection of inner automorphisms. And that was a little bit tricky to figure out, but we have a theorem that says that if you take the center of the group, so the set of all things that commute, and you mod that out of the group, what you get is something that is isomorphic to the set of inner automorphisms on G. Let's think about why this is, as opposed to going through the proof, which you can go read in the book. This definitely worth your time, but let's think about this intuitively. Why is this so? Well, ZG is the set of all things that commute, things in G that commute. The things that commute with everything else in G, so let's say I take some G that's in Z of G, and then I look at G, X, G inverse, this transformation here that takes X to GX, G inverse. Well, since that G commutes with everything, I can move that G inverse to the left, and what this turns into is just the identity map, because the G and G inverse can cancel because of commutativity. So if something's in there, it doesn't give us anything interesting other than the identity mapping of G back onto itself. So what if we say, hey, let's remove that from consideration. Let's remove commutativity from the picture and look at all the maps essentially of elements that don't commute. And so when we produce this G mod ZG, this is the set of all G times ZG, and it's the set of all cosets. And if G is already in Z of G, then it's going to get sucked into here. And your identity element is just going to be Z of G. If G does not commute with that, we essentially have this critter, GZ of G, that doesn't commute with a different element as long as this H is a completely different representative. So I have two different cosets here. Those will not commute. And they won't commute, at least they won't commute with everything in G. So when I form a map like this, out of one of these guys, then it's actually something other than the identity transformation. So let's take a look. What do we know? We had, what if I asked you, what is the collection of inner automorphisms on D4? How can we understand that thing? What does it look like? What is its group structure? Well, turns out that Z of D4 is this set identity rotation by 180 that I used in that example back there. So if I take D4 mod the center of D4, I get that group that we found back in the example. In other words, it's isomorphic to Z2 plus Z2. Now, what were those cosets? Remember what those cosets were inside here. You had just, let's call this H itself, but you had H, the center. You had RH, so rotation by 90 degrees. This is nothing. Don't do anything. Just leave it alone. This is rotation by 90 degrees. This is flip it over that diagonal. And then you can, let's see, how did we do that? We had tau row. I think we don't. I think we went like that. Did we have tau first? I just got to look back at that table just to make sure I'm keeping notation. Yep. So then we had tau row H. So this was transpose after rotating 90 degrees. And none of these operations will produce something that differs by 180 degrees. Yeah. So these are all the different ways that we can tweak things in here. And oh, sorry, I'm just starting to ramble. That I don't know where I was going with that. But what we can think of here as this is like your you, Z2, this could be zero or rotate, and then this could be flip or don't flip. So when I say zero, I mean identity. And this could be this or flip, and then I could possibly have a combination of those two things, which is a flip rotate. And yeah, I think that's about all I want to say about that guy right there. There is one last little result that I do want to prove. I think, all right, I'm just checking out my notes here. There's going to be some stuff that I ask you to show um, on the final, as I mentioned before. But primarily, I want you to understand this group structure that's being formed here and what it means to mod something out. There's a lot. I mean, we could spend a month proving things about this. But for those of you who are taking that second semester of algebra, we want to get to a certain spot. And that's what I'm hoping to pick up with on Wednesday. So I'm praying that you followed this, and if you have any questions, shoot me an email or we can talk on Wednesday. So I hope you're all well. Thanks for working with me on this odd remote kind of day, but I was happy to stay home and it felt like the right thing to do. So I'm gonna hope the same for you, and I'll see you soon. Bye bye, friends.